Okay, welcome everyone. We're very happy to have Derek Driggs today. So Derek is a final year PhD student and a Gates Scholar in Applied Maths at the University of Cambridge. His research is at the intersection of optimization and machine learning with a focus on developing algorithms in image processing applications. And today he's going to talk about barriers to deploying deep learning models during the COVID-19 pandemic. So thank you, Derek.
Thanks. Yeah, thanks for the introduction, and thank you for having me speak in this seminar series. So I'm really excited to be here, and I'm talking about some gaps in research that can be filled to help develop deep learning models for healthcare use. And specifically, I'll be focusing on the efforts during the COVID-19 pandemic to develop machine learning models to help clinicians, and whether these models were successful, and how we can use this pandemic as a study to help it make better models for healthcare in the future. So I'm really passionate about this topic, and I'm really excited to be talking to all of you about it today. Okay, so first I want to introduce the AixCovid Collaboration. So this is a collaboration of researchers I've been working with since March of 2020, when the COVID-19 lockdowns started affecting the UK. So this investigation is led by the University of Cambridge with my supervisor, Carola Schoenlieb, as a principal investigator, and also Ives Sala from the radiology department of Cambridge. And we've found collaborators all over the globe and from all different disciplines. So we have all of them listed here. You might recognize Matthew Thorpe as on this committee for the seminar series. And there might be some other people in the audience from this collaboration. But it's been a really nice team of people to work with. So it's rare that you get the opportunity to work with people from radiology and clinicians and math and statistics all under one roof. So it's been great working with all these people. And I also want to highlight a few of our data contributors, especially Adam Brooks Hospital in Cambridge, and the NHSX and British Society for Thoracic Imaging. They've provided a lot of the data that I'll be talking about in the talk today. And I also want to recognize some of our industrial partners in this collaboration. So we've been working with a number of different universities, mostly throughout Europe, and some corporate sponsors, as well as the NHS in the UK. And they've all been very important to keeping this collaboration going and doing the research that I'm going to present. So a huge thank you to all of them. Okay, the AixCovid Collaboration, our goal is to take a lot of different data streams describing COVID-19 patients and use these data streams to train models that will be helpful to clinicians during the COVID-19 pandemic. So we're looking at 6 main data streams: CT imaging, X-ray imaging, clinical data, calcium scoring of the heart using CT imaging, blood count data, and also quality control for all of these data streams. And obviously not everyone can work on all of these different projects at once because there's a lot going on, but I'm at the intersection of chest X-ray and clinical data. That's where I've been spending most of my time. And my goal is to develop a model that will help clinicians with resource management using X-ray, maybe some CT scans and clinical measurements. And so we want to, from this data, determine who will need oxygen support and who will need ventilation so we can distribute scarce resources better. So that's the end goal of this collaboration. And here is a timeline of what we've been working on up until the end of last year. So we all got together in March of 2020 at the beginning of the lockdowns, and we were able to obtain data fairly quickly. So we got our first data in April, and we got data from the UK in June. And that's really it's very surprising that we were able to get data this quickly. And it's because of the hard work of our collaborators at the NHSX and Adam Brooks Hospitals. And we rushed ethical approval, and we were able to get data released very quickly. So we were able to start with model development fairly early on in the pandemic. And while we were developing our own model, we noticed many other groups were also developing models to do similar things all around the world. And so we decided it would be a good idea to review this literature systematically. And so we submitted a systematic review of almost 1,000 papers in August of 2020. And this review will be the basis of my talk. So my talk today won't be about models, it'll be about methodologies and how we can develop models responsibly. Okay, and just to get everyone on the same page before I start describing these approaches, I want to give like a prototypical example of what these models look like in our collaboration and also all over the world for similar models and similar use cases. So in our collaboration, we sourced our data mostly from the UK to begin with, and we obtained maybe 3,000 COVID-19 positive X-rays and maybe 3,000 more COVID negative from the same hospital. We implemented extensive quality control, whittling down the usable images to maybe 4,500. And we had about a 1-to-2 ratio of COVID positive to COVID negative examples. And for validation, we just used 200 randomly chosen scans to test the model that we developed from the training data. And I won't talk about models very much in this talk, but we used a dense net architecture to begin with because it's been shown to be state of the art on classification tasks involving X-rays. And this is shown, I'm referring to a paper called CheckSpurt, which did a systematic study of many different machine learning models and deep learning architectures for X-ray classification problems. Okay, and because we didn't have much data to begin with of COVID-19 patients, we pre-trained our model using the CheckSpurt dataset, which is a huge public dataset of over 200,000 X-rays of patients with all sorts of different pathologies. And we use this pre-trained model as a starting point to fine-tune our model on the COVID-19 data that we obtained. We also found it was important to perform segmentation of these images so that we could localize the model to focus on the lung tissue to give more robust predictions. And I'll talk about that a little bit later on as well. Just to give a rough idea of our initial model's performance, this is the receiver operating characteristic curve. So we obtained pretty strong results. So an area under the curve of in the high 80%. And if we compare it to radiologist performance, we perform much better than radiologists. Now we measured radiologist performance using the NHSX dataset, where there were a lot of indeterminate labels. And depending on how you interpret the indeterminate labels, it'll give you a different measure of the radiologist performance. But in either case, we performed much better than the radiologists in this prototypical example. Now we want to make sure our models aren't biased, so we performed some analyses of our bias in the data set. So we found without segmentation, if we look at heat maps to see where our model is looking when making a prediction, the model focuses a lot on annotations on the scans. So for example, if the X-ray is taken while the patient is in the supine position, the model focuses on this information. And we found that this could be because patients in the supine position, when they're taking an X-ray, are of poorer health and are more likely to have severe COVID-19. So a machine learning model will pick up on this information and they'll cheat using outside information if they can. And if we perform segmentation, we can localize the model to give most importance inside the lung tissue, which is what we would like to see. All right, so this was a very, very quick description of a prototypical model that formed the basis of our review. So many different research groups performed similar studies that looked like this. And the question now is if this model is ready to be deployed. So it seems to have very strong performance on our validation set. but there might be some concerns that we have to address before the model is deployed. Some questions we might ask is this model useful for clinicians? Do clinicians need a diagnostic model like the one we've just built? Was our data sourced correctly, and did we follow all the ethical agreements, and were we able to obtain ethical agreements in a reasonable time frame? Did we perform a correct amount of quality control on the data? Is it large enough? And are there biases in the data sets that we couldn't find with our initial bias investigation? And finally, was our validation, did it give a good enough judgment of our model's performance? Will our model be robust? So we didn't perform external validation. We used our training data and test data from the same source and just split it into training and testing. So we didn't perform external validation. And how does that affect our model's generalizability and consistency? So these are all questions we need to consider before we deploy our models and before any models that are developed in this similar way should be deployed. So we got done creating this prototypical model, and we started looking around at what other research groups have done, and they've done similar things. And we started to wonder how our research is affected by the fact that we're working in a time of crisis. So in April of 2020, Professor Julia Gog, who's an expert in disease modeling, published a short opinion piece in Nature about how researchers can contribute their research during the COVID-19 pandemic and how to have the best positive impact during this pandemic. She made two important points. So instead of adding to the noise, it's best to amplify the signal that exists already in the research. That it could be a very helpful contribution that researchers can make. And everyone's instinct might be to start by training your own model, but it might actually be better to consider other ways that one could contribute with research skills. And so this paper really forms the ethos of our review, and it was really the genesis of our review. And we wanted to figure out how we could amplify the signal, and by doing so, really learn what it means to create a machine learning model that could be deployed for healthcare purposes. And along the way, we found out that it's very difficult to create a trustworthy model, and there are gaps in research that we could fill to help machine learning models be deployed to help clinicians, not just in the COVID-19 pandemic, but beyond the pandemic for other use cases as well. Okay, so some questions that we wanted to answer in our review are these thousands of papers developed that create a machine learning model for COVID-19 diagnosis or prognostication, are they trustworthy? Some of these models have actually been deployed. What are the consequences of this deployment? And what makes these models different from the ones that cannot be deployed? Are there any differences between these two models? And finally, how can machine learning researchers best contribute now and in future crises? And this is the flow and the results of our review. So we started with almost 1,000 papers related to machine learning using imaging features for diagnosis or prognostication of COVID-19 patients. We found only 29 papers had sufficient documentation to be reproducible, and we used standard checklists, the claim and RQS checklist, to evaluate reproducibility, and I'll show what those checklists look like on the next slide. We found that of these 29 papers that are reproducible, many of them contain severely biased data sets. There's a huge reliance on Frankenstein public data sets, which I'll define later. Many models don't make their code, or many papers don't make their code or models open source, and many don't have any external validation, which makes it less likely that their model performance will generalize to new scenarios. And most papers have no sensitivity or robustness analysis. So we determined that none of these models are clinically useful. And this might sound like the end of the story, but this is really just the beginning of the story. So we need to figure out why these models aren't clinically useful and how we can make them clinically useful. So the last thing we want from this review is for researchers to think that there's no use in pursuing problems like these. So we also want to figure out how can we quantify how far away we are from developing usable models and close that gap. So create a process to develop usable models. All right, and to give you an idea of the checklists that we use to evaluate these models, the first one is the checklist for AI medicine, or CLAIM checklist, and we use this mostly to determine if a model is reproducible. And so these are some metrics that the checklist includes. And then another one we use is the Radiomic quality score. So it's a checklist that's used for medical models that use radiological data. And I've highlighted one of these that'll be important for our discussion. So this checklist wants to combat overfitting by decreasing the number of parameters compared to the number of examples that you have. And this checklist states overfitting is inevitable if the number of features exceeds the number of samples. So we'll revisit that point later. And the PROBAS checklist was the last checklist we used, and it measures the risk of bias in a model, specifically for medicine. And one of the points on this checklist is, were the predictors excluded from the outcome definition? And this is related to incorporation bias, which is a bias that you don't see studied much in the context of machine learning. But we found machine learning models were very prone to fall victim to this type of bias. So we'll be revisiting this later in the talk as well. All right, and to begin, I want to talk about purely sources of bias in existing research. So reproducibility issues aren't really the interesting point of our review. One of the interesting points is the bias. And so sources of bias are receiving a lot of attention in machine learning models today, because people are finding that the way we're developing machine learning models might not be robust to, or immune to types of biases in data sets that we're using to train these models. So I'm going to start from obvious sources of bias to more nuanced sources of bias and room for existing or further research in this subject. Okay, so this image on the right here shows examples of images taken from different classes in a representative example of a study that develops a machine learning model for COVID-19 diagnosis. So we see patients with normal X-ray scans here, COVID-19 X-rays here, and then bacterial and viral pneumonia. So there are huge areas of bias that you can see just from these representative examples from each of these classes. And so usually at this point in my talk, I stop and hear if the audience has any ideas of what types of biases might exist here. But because of the online format, I think I might just share with all of you what I've heard from other machine learning experts when I give them this task. So other machine learning experts notice that this image, for example, is flipped horizontally. So the heart extends into our left of this image, where usually it goes to the right. So that could be a source of bias, and that's definitely true. Another thing that someone has pointed out is the L in these can be flipped. And that's definitely true. The L isn't in a consistent placement for all the images, but there's actually one huge source of bias that becomes more obvious if I put this picture up next to this picture. And this picture shows an infant receiving an X-ray. And because infants are wriggly, you have to put them in this little cylinder and keep their arms out of the way while you perform the X-ray. And you can see in these two classes, the viral pneumonia and bacterial pneumonia classes, you can see the patient has their arms up and the patient has sort of a rotund infant torso. And you can tell that these two classes are made up of mostly pediatric patients. And so this seems like this is obviously a huge source of bias, and it's hard to believe that this crept into a published study. But it actually makes more sense when you consider the scarcity of data for COVID-19 patients. And so people are using whatever data they have available. And one huge data source is this data set from Kermany et al. That includes bacterial pneumonia and viral pneumonia, patients with these conditions, and they're almost all pediatric. And so in the absence of better data, researchers turned to this data set and ignored the fact that COVID-19 patients with severe COVID-19 rarely are pediatric. They're usually much older. And so if a model that appears to detect COVID-19 is actually just detecting age when you train it with this data, it's reasonable to believe that that's what the model is detecting. So there are a lot of demographic differences that are sources of bias. COVID-19 patients are consistently older than patients in other classes, and we talked about that already. But also, most data, especially at the beginning of the pandemic, came from China, and most models are intended for Europe. So China could have completely different data collection strategies or use different scanners that could make the X-rays different in ways besides the presence of COVID-19. And in fact, there is one huge difference between practices in China and practices in Europe. And that is that in China, CT scans are the first line of defense when diagnosing a patient with COVID-19, where in Europe and in the Americas, X-rays are more popular. So all of these need to be taken into account when you develop a model, and you want to make a model that isn't biased. And so you have to understand these differences in the demographics of the data that you're sourcing to train your model. Okay, so that was one huge source of bias, demographic differences. Another huge source of bias is that the train and test splits are often not performed at the patient level. And this is true even in very popular public data sets where the train and test splits are given to the user. So in public data sets of COVID-19 patients, it's often true that there's a patient with scans in the training set and in the test set, which can give an inflated performance metric for the model because the model sees the same patient at training time and at testing time. So it's an easier problem to solve. So trustworthy studies partition even at the institutional level. And this is related to using external validation, which is a very important quality of high performance models that can perform robustly. So most checklists used in the medical community require external validation or a partition at the institutional level. And these partitions aren't even at the patient level in most cases. So that's also a huge source of bias. Okay, and finally, I want to talk about Frankenstein data sets, these public data sets that I mentioned. So Frankenstein data sets are what we call public data sets that were combined and released under a new name. So it was actually common practice for researchers to collect a lot of public data and then release it as a new name when they release their model. And this is fine, except other researchers are now using this public data set to test their model without understanding that they use similar data to train their model. So they use a subset of the testing data to train their model, and they don't realize this. So it gives a hugely inflated measure of their model's performance. And there are also many other issues with these public data sets. Many of them comprise pictures of scans that are published in journals. So in medical journals where radiologists are investigating presentations of COVID-19, researchers have used automated approaches to extract images and then extract labels using natural language processing, which can lead to noisy labels. And it also leads to selection bias because authors publishing their work in medical journals choose to present interesting examples. They don't present general examples in a lot of cases. So this could maybe make the images that represent COVID-19 class more severe. And also you lose a lot of image quality. So the resolution is reduced, Hounsfield units are lost, the original DICOM file is lost. And very recent research coming out this year and at the end of last year suggests that using pictures of pictures can degrade performance of predictive models that are trained on imaging features. So all of these are issues and can cause a model to not generalize its performance when actually deployed. So all of these need to be under consideration. Okay, and the final source of bias I'm going to mention is a huge one, and it's very subtle. So the last few, I structured this talk to go from obvious sources of bias to subtle sources of bias, and I think this is the most subtle and the most important. It's called incorporation bias, and incorporation bias arises in a model if the labels are not independent of the predictors in its training data. So for example, if a COVID-19 classifier, if those labels were determined from imaging features using clinicians, then this leads to incorporation bias because the imaging features are the predictors in your model. So incorporation bias has been studied a lot in the medical community because it happens all the time where a medical model might be trained using clinicians to give the ground truth labels. And then the clinicians consider all sorts of clinical aspects of the patient when making this decision. And so it's likely that the clinician is considering predictors that are input into the model. And it can severely affect a model's generalizability. And actually, models depending on imaging data or other subjective features are particularly vulnerable to this type of bias. And this is well known. This is mentioned in the ProBAS tool. Okay, and I also want to mention that this bias is a spectrum. So it's not that incorporation bias exists or it doesn't exist in your model. It's a sliding scale. So if you have patient outcome as a label, that's generally considered bias-free. So if a patient dies, that's not a predictor, that's input to another model. It's independent of any predictor. You know it's objectively true. But ventilation, if a patient goes on ventilation, that might not be free of incorporation bias because when a clinician decides to put a patient on ventilation, they look at all sorts of aspects of the patient, including imaging features. And so there could be a threat of incorporation bias, but we would consider this a low threat of bias. So it's a sliding scale, and it's difficult to eliminate completely in a lot of cases. And I just want to give a few examples of where we found incorporation bias in a lot of existing works. We already talked about COVID-19 labels being determined from imaging features. So in this work I cite, they acknowledge the fact that this leads to incorporation bias, and they say they use silver labels and gold labels, where the gold label is determined from a PCR test, which is independent of the imaging features, and the silver labels are determined from the imaging features. And they find that their model shows or seems to have better performance when trained using silver labels. And it's unclear if that's because different data is being used or if it's because of incorporation bias, but I personally suspect the latter. We also saw it when researchers used the full data set to train a segmentation model and then input the segmented images into their classifier. This leads to incorporation bias because the segmentation model has seen the labels of the data. So it's seen COVID-19 patients, and it knew that these were COVID-19 patients, and that's how it learned to segment those images. And so the labels are not independent of the predictors anymore. And another example is using a GAN for data augmentation. It seems natural that you might want to produce more COVID-19 patients or examples using a generative adversarial network. But if you do this, you're at risk of incorporation bias because the GAN determines the label of the images it produces from the imaging features. So it sees a lot of COVID-19 imaging features, and then it creates another one that is labeled COVID positive. So the labels are not independent of the predictors in your data set. Okay, and one interesting implication of this incorporation bias is that it is potentially inappropriate to try to replicate radiologists when developing a model. So if your labels are determined by radiologists from imaging features, and then you're inputting those imaging features into your classification model, that puts the model at risk of incorporation bias. So the aim should not necessarily be to replicate radiologists, but it should be to determine some sort of classification that is whose labels are independent of the predictors. So this definitely could use more research in the machine learning community in this context. So it's well understood and it's been studied a lot in the medical community, but I haven't seen many papers in the machine learning community discussing the implications of incorporation bias. Okay, so that covers all of the sources of bias that I wanted to talk about. And now I want to talk about gaps in research that are preventing deployment of these models. And we touched on a few already, but there are a few more I want to talk about. And this is important because if we can close these gaps with further research, I think we have a much better chance of creating models that can be deployed responsibly in the clinic. Okay, so some of these gaps that need to be filled are disconnects between the machine learning and medical communities. So many models, machine learning models, address irrelevant problems for clinicians. So there's a huge focus right now on the diagnosis of COVID-19 using machine learning, but clinicians don't need help separating critically ill patients with COVID-19 from healthy people. That's sort of an easy problem. What's important and what clinicians could really use is a way to decide how to distribute scarce resources. So from a model that does something like severity prediction, how do we decide who gets oxygen and who gets ventilation, especially when these resources are scarce? It would be great to have help with that decision. Another disconnect is that target populations and the intended use of the models are often poorly defined. So in the machine learning community, it's not really too big a problem if you didn't exactly describe what your intended use in the clinic for your model is, or what the exact target population is, because we're more interested in developing models that work. So if we show our model works, then we don't always define exactly the problem that it works for. So for example, recent research has shown that about half of asymptomatic COVID-19 patients have changes on their radiographs. That means half do not have any changes. And other works have shown that half of patients with COVID-19 have normal CT scans at the beginning of the disease. So with these two facts known, are we really performing diagnosis when we create a diagnostic model? We're not diagnosing the general population with COVID-19 or as healthy. We're working within a subset of this population. So we're working within a subset of people that have changes on their x-rays or CT scans while having COVID-19. And this distinction is really important, especially when we consider deploying a model. We can't just feed anyone into this model and expect the classification to be correct. We have to precisely define our target population. Okay, and lastly, machine learning experts, when developing models, might not pay attention to radiologists and their recommendations. So at the beginning of the pandemic, institutions like the American College of Radiology said that CT scans and x-rays should not be used to screen or as a first-line test to diagnose COVID-19. And then these institutions have since softened their stance because PCR testing, which is the gold standard for determining if a patient has COVID-19, can take a long time, and these tests can be scarce resources. So these views have softened, but they should be acknowledged when developing a model. Okay, so these are a lot of disconnects that exist between the machine learning and medical communities. And there are a few more and that really can prevent a model from being deployed. We talked about this already, but medical studies require external validation rather than the usual train test split that's taught in Machine Learning 101. So the data that you use for testing should come from a completely different source than the data that you use for training in order to guarantee that your model is robust. Also, medical studies follow strict reporting criteria like those we've talked about. And this is less true in the machine learning community. And then finally, there's also a converse effect as well. So in the medical community, measures of generalizability and interpretability of a model might not be appropriate for deep learning models. So for example, if you remember back at the beginning of my talk, I highlighted one of the points on the RQS checklist that says you need enough examples or events per trainable parameter in your model, or else the model is guaranteed to overfit. And this is sort of a touchy subject in deep learning because you have millions of trainable parameters and then you're fine-tuning it on just a few thousand scans. But in many examples, we've seen that deep learning models can still generalize even if the events per variable is small. So I think this EPV is an archaic metric, and the two communities, machine learning and medical, need to come together to figure out what is actually an appropriate metric to determine if a deep learning model is overfitting. Okay, so there's a lot of communication that's required between the ML and medical communities to create a bridge that can lead to a deployable model. And also we've noticed that in a crisis, open problems in machine learning don't receive any consideration. So they're very important right up until you're creating a model to be used in the crisis, and then they don't receive any discussion. So we talked about this, pictures of pictures hurting model performance. There's recent research on this showing that this is a real effect, and we need to take this into account when we're sourcing our data. Many researchers agree that there's distribution shift when you move from one country or hospital or even scanner to another one. But the research community we don't agree on how that would affect a model's performance or how to adjust for this distribution shift. So that requires further research. And also presentations, especially of COVID-19, could evolve over time. And this needs to be taken into account in models that are deployed. So some of the best machine learning models for COVID-19 severity prediction that have been released recently actually use time series of data in order to capture this effect of evolving presentations over time. Okay, other open problems that are crucial to developing deployable machine learning models involve interpretability. And so I'm sure we all know deep learning models are notorious for having poor interpretability. It's hard to understand how they're making their choices. So very recent research has shown that saliency maps might not highlight relevant regions when performing diagnosis of a chest X-ray. So that's important, and that requires further research to understand how these models are then making their choices. Model calibration and confidence scores could depend on local disease prevalence. So a lot of models are tried to be more interpretable for clinicians by giving confidence scores, but it's unknown how these scores change when the prior distribution changes within the population. So that is an open problem as well. And also, how do we incorporate clinical information with this imaging information? It's still an active area of research to figure out the best way to incorporate clinical information, but this should be the end goal of these models because a radiologist would have access to imaging features and clinical information. So we would want to develop a model that uses both data streams as well. Okay, so I discussed sources of bias, and I have discussed a lot of open problems and disconnects between the machine learning and medical communities that we could fill to create a pipeline for developing deployable machine learning models, but it requires more research. We need research in this area to close these gaps. And while some of the problems that I highlighted, especially towards the beginning of the talk, can be filled today, there are a lot of problems that can't be solved without more investigation and further research. So I just want to talk about the conclusions of our review. So we started this review with some questions, and we want to know 1 year after Professor Gog published this paper telling researchers how they might be most effective during the COVID-19 pandemic. 1 year later, have we been effective? Have we followed her advice? So are existing models trustworthy? We found that many models, including published works, have serious methodological errors and sources of bias. The biggest, and to me most interesting, is incorporation bias. So some models have been deployed. What made these models usable? So we found in models that have been deployed, they do seem to have external validation on high quality data sets. And that's partly because they were deployed. So they're able to collect data in real time and see how their model performs on data that's sourced in a prospective rather than retrospective fashion. So that's one big difference. But also we found sources of bias and issues in deployed models as well. And finally, how should machine learning researchers continue to contribute in this pandemic and in future crises, or even in developing healthcare models to be used in healthcare in the future? And so the most important thing is to amplify the signal of the existing literature. This is a hugely important thing that people with research skills can do if they want to contribute during a crisis like the COVID-19 pandemic. Okay. And now I want to give a few recommendations so we can close the gap that exists that prevents deployable models from being developed. Our first recommendation is to work with clinicians when developing these models and focus on answering clinical needs. We generally do not need diagnostic models, and it's important to know things like what is the primary data source in your target population so your model can be as effective as possible. It's also important to source original data. We talked about all sorts of issues with public data sets, including the Frankenstein data sets. And it's also important to acknowledge the small data problem during model development. So use feature reduction, use semi or self-supervised learning. And just because this small data problem exists doesn't mean there's nothing that we can do about it. So acknowledge it's okay to use data that is less than perfect if we can acknowledge the problems with the data. And then we can learn as a community how to overcome these issues to create a model that can still work. Another recommendation is to follow and improve medical research standards. We talked about 3 different checklists that are common practice to follow when developing medical models, and the machine learning community hasn't really rallied behind these checklists yet, in my opinion, but there are also issues in these standards. We talked about events per variable being an archaic metric, so we need to figure out how we can actually measure overfitting and generalization in deep learning models, and what is an appropriate metric here. Okay, I'm going to get some water really quickly. All right, 2 last points. Researching better models will always be important, but on top of this, we need more researchers filling the gaps that currently exist that prevent deployment of these models. So we talked about this already, that some of them can be filled today just by following good research practices, but some actually need new ideas and new research behind them. So this is an important area that's open for research. And finally, there are many uses of machine learning in healthcare outside of diagnosis and prognostication. So if you want to help clinicians during a crisis like the COVID-19 pandemic, you don't just have to make a diagnosis or prognostication model. And I want to give an example from our collaboration on what we're doing with developed machine learning models to help clinicians right now. So I'm going to talk about deploying a model in the lab rather than deploying it in the clinic, and what we can learn by deploying models in the lab. Okay, so I'm going to tell a brief story about what our collaboration is working on right now. So at the beginning of the pandemic, some researchers, some clinicians, a few from our collaboration noticed that COVID-19 patients experience higher rates of pneumothorax, which is a collapsed lung. So you can see it in this image of a COVID-19 patient. And it outlined is a gap because the lung is collapsed. So this patient has pneumothorax. The increase in pneumothorax prevalence is not explained by ventilation alone. So patients on ventilation are more likely to develop a collapsed lung, but this doesn't explain the disconnect here with COVID-19 patients. And we would like to determine what causes this pneumothorax in COVID-19 patients. So this is an interesting question for clinicians. And it's hard to study because fewer than 1% of admitted COVID-19 patients admitted to a hospital have pneumothorax. So to find a lot of examples of pneumothoraces, clinicians would have to study many X-ray scans and figure out which ones are of patients with a pneumothorax. And this is a very time-consuming process. So we thought we could automate this process and tell clinicians which scans to prioritize by using a deep learning model. So we trained a DenseNet model on the CheckSpert dataset to detect pneumothoraces. And we validated it on 8,000 scans from the NHSX and Adam Brooks hospital datasets that we have access to. And we found on this dataset, this external validation dataset, it performed pretty well with area under the curve of around 90%, 91%. And we're using it now to prioritize which scans should be seen by clinicians, about 30,000 of these scans. So hopefully we'll find that 1% of this 30,000 has pneumothorax. And so we can better study what the origins of this pathology are. Okay, and so the benefits of this automated prioritization is that we can get more scans with less time. That's the end goal here. So previous studies looking at pneumothorax in COVID-19 patients include only about 71 patients. And so if we can get 1% of these 30,000, then we would have 3,000 scans, and we can study this pneumothorax issue in COVID-19 patients much more closely. And to give you an idea of the time that we're saving clinicians, developing that validation set of 8,000 scans took several weeks to do quality control and locate the pneumothoraces. And it was a very time-consuming process. And CT scans are even more costly. So the idea is we would use this model to look at patients most likely to have pneumothorax on an X-ray. We would make sure, a clinician would check to make sure that this is in fact a pneumothorax example. And then we would use the associated CT scan to really see to really study how this pneumothorax came to be and why it's so prevalent in COVID-19 patients. Okay, and the benefits of deploying this model in the lab rather than deploying it in the clinic is clinicians become more comfortable working with these models. So they become comfortable interpreting these model predictions. And we can learn what clinicians like to see in these models and what models are useful to clinicians. We can also study how models perform in a prospective environment rather than a retrospective environment. So we're taking new data in, but in a laboratory setting, and seeing how the model generalizes its performance. And lastly, this type of deployment is low stakes. No patients are at risk. And even if the model performs very poorly, it can still help clinicians. It can help prove hypotheses. So for example, if we have this hypothesis that pneumothorax is more prevalent among patients with COVID-19, even a model that's slightly better than guessing would save clinicians time in determining if this hypothesis is true. Because without a model, a clinician would just choose a sample at random evaluate which have pneumothoraces, and then we can either accept or reject the hypothesis that it's more prevalent in patients with COVID-19. But with a model that's slightly better than guessing, we choose the scans that the model prioritizes first, and we can choose to stop at any point looking at scans, assume the rest of them do not have any pneumothoraces, and then we can still prove the hypothesis that pneumothoraces are more prevalent in COVID-19 patients. So for both of these reasons, it's a very low stakes procedure. And it only helps that our model seems to perform very well at this problem. All right, and in conclusion, I want to say that creating machine learning algorithms for clinical practice goes hand in hand with using machine learning to understand COVID-19. And there's been a huge focus of developing models to do the former and very little focus on developing models that do the latter. I also want to say that the technology exists to create useful models in healthcare and to help clinicians during the COVID-19 pandemic. So we don't necessarily need technological advancements to create useful machine learning models in healthcare, but we do need more research in developing and using existing technologies responsibly. I also want to highlight that machine learning models should be developed with similar care to how vaccines are developed. And I recognize developing a vaccine is very different than developing machine learning model. But what I want to say with this statement is there should be a procedure in place to deploy a machine learning model in healthcare that's similar to how there is a procedure in place for a vaccine to be distributed. And we should know that a vaccine is safe or a machine learning model is safe just in the same way. There needs to be a procedure in place to do this. And it would hugely help during the next pandemic or for creating machine learning models to help in other areas of healthcare. And this really is a test case for applying machine learning in healthcare, and the world is watching right now to see how machine learning can help in this COVID-19 pandemic. So if we can successfully deploy a model, I think that would do, it would have a lot of benefits for advancing machine learning in healthcare. And conversely, if we fail to develop good research practices in this environment, then it could set back research in this area. So it's a high stakes area of research right now, in my opinion. Okay, and I want to leave you saying that we're happy to collaborate with all sorts of researchers. So if you're interested in getting involved with this collaboration, we're always looking to work with clinicians and data contributors especially, and also other groups that can augment the algorithmic approaches that we're taking on any of our data streams. If you want more information, here's the link to our website. And here are a review paper and the editorial that most of this talk comes from. And I'm really happy to be here, and I'm glad that you let me give you this talk. And I'm happy to receive any questions that anyone might have.